I'm about to put forward a viewpoint that may come across as gloomy, perhaps even unsettling, but I believe it is the most reasonable conclusion we can draw from modern physics, biology, and our current understanding of the cosmos. The emergence of intelligent life appears to be incredibly improbable, far more unlikely than most people realize. It's possible that humanity is the only intelligent species in our entire galaxy. It's even possible that we are the only intelligent beings in the entire observable universe. The profound quietness we encounter when we search the heavens for signs of alien communication, that overwhelming cosmic stillness, may not be the result of poor search methods or incorrect frequencies. It may simply be that there is no one else out there at all. My name is Leonard Susskind, and I've spent my professional life studying the universe, from the tiniest subatomic scales to the vastness of cosmic space. Over the years, the more I have learned, the more I have come to appreciate how extraordinary, delicate, and unlikely the rise of intelligent life truly is. A good place to begin is with the Fermi Paradox, because this is where the entire conversation about extraterrestrial life really starts. In 1950, physicist Enrico Fermi was having lunch with colleagues at the Los Alamos National Laboratory. The group was casually discussing flying saucers and the possibility of alien civilizations. At some point, Fermi posed a straightforward but powerful question. Where is everyone? What he meant was this: our galaxy is roughly 13 billion years old and contains somewhere between 100 and 400 billion stars. We now know, thanks to missions like Kepler and TESS, that a large number of those stars have planetary systems. If even a small percentage of those planets developed intelligent life, and if even a fraction of those civilizations achieved space travel, then the galaxy should already be filled with visible signs of their existence. They should have spread across star systems, launched exploration probes, built massive technological structures, or at the very least, left detectable radio signals. We ought to observe something, some trace of their presence. Yet, we see nothing. No transmissions, no spacecraft, no alien artifacts, no evidence of advanced engineering. The universe appears completely silent. That contradiction is what we call the Fermi Paradox. If intelligent civilizations are likely to exist, why is there no observable proof of them? Over the years, scientists and thinkers have proposed countless possible answers to this paradox, literally hundreds of different explanations. But I want to focus on one specific type of solution, the one I personally find the most convincing. That possibility is simple. Intelligent life is extremely rare, perhaps so rare that it has only appeared once. This idea runs counter to the Copernican principle, the long-standing assumption that Earth is not special and that we occupy an ordinary planet orbiting an ordinary star. For much of my life, I accepted that principle without hesitation. I assumed that intelligence must be widespread simply because the universe is so unimaginably large. But as my knowledge has deepened, my perspective has gradually shifted. To explore this more clearly, it helps to look at the Drake equation, which provides a structured way to estimate how many communicative civilizations might exist in our galaxy. In 1961, astronomer Frank Drake introduced an equation designed to break the problem into smaller, more manageable parts. The equation is written as n equals r asterisk times fp times ne times fl times fc times lphi. Let me explain what each term represents. N is the number of civilizations we might be able to detect. R times is the rate at which new stars form in the galaxy. Fp is the fraction of those stars that have planetary systems. Ne is the number of planets around each star that could potentially support life. Fl is the fraction of those planets where life actually appears. Fi is the fraction of life-bearing planets where intelligence evolves. Fc is the fraction of intelligent species that develop technology capable of being detected. And L is the length of time those civilizations emit signals into space. Now, if we tried to estimate some of these values, things initially seem encouraging. The star formation rate in our galaxy is roughly 1 to 3 new stars per year, a figure we understand fairly well. The fraction of stars with planets, Fp, appears to be close to 1. Observations suggest that almost every star has at least one planet. Ni, the number of potentially habitable planets per star, is harder to pin down, but current estimates range between 0.1 and 0.4. That means somewhere between 10 and 40% of stars could host a planet in the so-called habitable zone, where liquid water might exist. Up to this point, the numbers seem optimistic. There could be billions of worlds in our galaxy with conditions suitable for life. But this is where the certainty ends and the real unknowns begin. The next term, Fl, the fraction of habitable planets where life actually arises, is something we have almost no concrete information about. At the moment, we only have a single example to study Earth. Life appeared here roughly 3.8 billion years ago, not long after the planet formed. Does that mean life emerges easily wherever conditions allow, or were we simply incredibly fortunate? The truth is, we don't know. Estimates for Fl, the fraction of habitable planets where life begins, vary wildly. Some scientists argue it could be close to one that nearly every suitable planet develops life. Others suggest it could be as low as 1 in 10 billion or even rarer. That represents an uncertainty spanning many orders of magnitude. Then we reach the next factor, Fi, the fraction of life-bearing planets where intelligent life eventually arises. And this is where I believe the real challenge lies. On Earth, life has existed for about 3.8 billion years. Yet, for the overwhelming majority of that time, around 3 billion years, life consisted solely of single-celled organisms. Bacteria and archaea dominated the planet. No plants, no animals, no complex structures, just microscopic cells surviving and reproducing. Then, around 600 million years ago, something remarkable occurred, the Cambrian explosion. In what was, geologically speaking, a very short period of time, complex multicellular life suddenly appeared. Animals with specialized body plans, eyes, nervous systems, and predator-prey relationships emerged. The diversity of life expanded dramatically. But here's the important question. Why did it take nearly 3 billion years for this transition to happen? We don't really have a clear answer. What we do know is that the leap from simple single-celled life to complex multicellular organisms was not easy or automatic. It required a very specific set of circumstances that may be extremely uncommon elsewhere in the universe. To understand just how unlikely our existence may be, we need to look closely at Earth's early history. For the first 2 billion years of life on this planet, there was no free oxygen in the atmosphere at all. From about 3.8 billion to 1.8 billion years ago, Earth's atmosphere was dominated by nitrogen, carbon dioxide, and methane. The oceans were filled with single-celled organisms carrying out anaerobic metabolism processes that do not require oxygen. Then, around 2.4 billion years ago, a pivotal event took place, the Great Oxidation Event. Certain microorganisms, cyanobacteria, had been producing oxygen through photosynthesis for hundreds of millions of years. At first, this oxygen didn't accumulate in the air because it reacted with iron dissolved in the oceans, creating vast layers of rust that sank to the seafloor. We can still see evidence of this today in ancient geological formations known as banded iron deposits. Eventually, however, the available iron was used up and oxygen began to build up in the atmosphere. This was disastrous for most existing life at the time. Oxygen was poisonous to the anaerobic organisms that had ruled the planet. In a sense, it may have been Earth's first great mass extinction, but it also opened the door to something new. Oxygen allows for aerobic respiration, a far more efficient way of generating energy. An organism that uses oxygen can extract roughly 18 times more energy from the same amount of glucose than one that relies on anaerobic processes. That extra energy is what makes large, complex, multicellular organisms possible. Yet even after oxygen became available, complex life did not appear right away. In fact, it took nearly another 1.8 billion years. One reason was that oxygen levels were unstable for a very long time. There was a long stretch in Earth's history known as the Boring Billion, lasting from about 1.8 to 0.8 billion years ago. During this period, oxygen levels remained stuck at perhaps 1 to 10% of modern levels, far too low to support complex animals. It wasn't until roughly 800 million years ago that oxygen concentrations began to rise significantly again. And even then, Earth went through another enormous crisis. The Snowball Earth episodes between about 720 and 635 million years ago, when the entire planet may have frozen over. Ice likely covered the oceans from pole to pole. Life barely managed to survive. Only after these catastrophes passed, after oxygen stabilized at higher levels and the planet thawed, did the Cambrian explosion finally occur around 540 million years ago. And this is what troubles me. There is no reason to assume this sequence of events had to happen. The rise of oxygen-producing bacteria, the Great Oxidation Event, surviving global ice ages, these were all contingent, fragile developments. They could easily have turned out differently. Earth might have remained a world inhabited only by bacteria forever. Even after complex life finally emerged, intelligence was still far from guaranteed. It took another 600 million years before a species like ours appeared. Think about that timeline carefully. Out of Earth's 4.5 billion year history, complex multicellular life has existed for only about 600 million years. roughly 13% of the planet's existence. Technological intelligence, on the other hand, has been around for only a few tens of thousands of years, about 0.007% of Earth's history. For more than 99.99% of the time, there was no intelligence here at all. No minds capable of asking questions, no science, no technology, just simple organisms surviving, evolving, and eventually giving rise to plants and animals, but never to thinkers. Now let's consider the evolution of intelligence itself, because this is another major obstacle that many people overlook. Intelligence is not an automatic outcome of evolution. It is not even obviously useful in most environments. Take dinosaurs as an example. They ruled the planet for about 165 million years, far longer than mammals have existed. During that immense span of time, with countless species evolving and adapting, none of them developed anything remotely comparable to human-level intelligence. Some dinosaurs were social. Some had relatively large brains for their size. A few may even have used primitive tools, but none built civilizations, created complex language, or developed advanced technology. Why not? Because intelligence is costly. The human brain consumes about 20% of our body's total energy, while making up only about 2% of our body mass. That is an enormous metabolic expense. For most creatures throughout evolutionary history, that cost simply didn't provide enough benefit. A predator does not need to be highly intelligent to survive. Sharks, for example, have thrived for around 450 million years with relatively small brains and simple behavior. Thriving as a plant-eating species does not require intelligence. Grass, for example, has spread across enormous portions of the planet without possessing a single nerve cell. Intelligence only becomes useful under very particular circumstances. Situations where problem-solving, cooperation, planning ahead, and the use of tools provide a real advantage. On Earth, those conditions happen to exist for one very specific group: early human ancestors living in the African savanna. These primates faced constantly changing environments. They benefited from working together, from developing better hunting strategies, from crafting simple tools, and from passing knowledge between generations. But that was just one evolutionary path, one lineage out of millions that have appeared and disappeared over the history of life. Out of all those countless branches, only one produced a species with truly advanced intelligence. There are certainly other intelligent creatures on Earth. Crows show remarkable problem-solving abilities. Octopuses are highly adaptable and capable of complex behavior. Dolphins display sophisticated social structures and communication, yet none of these animals ever built machines, developed technology, or created anything resembling a civilization. And there is an even deeper issue to consider. We often assume that intelligence and consciousness go hand in hand, but that may not actually be true. Consciousness, the inner subjective experience of being aware, might not even be necessary for intelligent behavior. It is entirely possible to imagine entities that behave in highly intelligent ways while having no internal experience at all. Philosophers sometimes refer to such beings as philosophical zombies, creatures that act as if they are conscious but feel nothing inside. We honestly don't know at what point in evolutionary history consciousness first appeared. Did the earliest animals experience anything? Do insects have subjective awareness? Do fish? These are questions we still cannot answer, and we have no idea whether consciousness is a required ingredient for the kind of intelligence capable of building technology and civilizations. All of this adds layer upon layer of improbability. Billions of different species have existed on Earth. Out of all of them, only one has ever developed advanced technology. Only one has built cities, created written language, and practiced science. Just a single species among an almost unimaginable diversity of life. The evolutionary biologist Ernst Mayr argued that this fact alone suggests intelligence is not an inevitable outcome of evolution. Most species survive and thrive perfectly well without it. Intelligence demands a large brain, and a large brain consumes enormous amounts of energy. For the vast majority of evolutionary history, that trade-off simply wasn't worth it. Mayr concluded that the value of Fi, the fraction of life-bearing planets where intelligence arises, must be extremely small, perhaps as low as 1 in a billion or even less. If that is correct, then even if life itself is common throughout the universe, intelligent life would still be extraordinarily rare. Recently, new research has made this picture even more discouraging. In 2024, two planetary scientists, Robert Stern and Terence Geria, published a study arguing that the traditional Drake equation is missing two critically important factors. They propose that the presence of plate tectonics and a balanced combination of continents and oceans may be essential prerequisites for the development of intelligent life. Plate tectonics, the slow movement of large sections of Earth's crust, plays a number of vital roles. It recycles carbon between the planet's interior and atmosphere, helping to regulate long-term climate. It creates varied landscapes such as mountains, coastlines, and valleys, which drive biological diversity. It may even have contributed to the rise of oxygen levels that made complex life possible. But plate tectonics is not something every planet will have. It requires very specific conditions. A planet must be large enough to maintain internal heat, yet not so large that its crust becomes too thick to move. It likely needs significant amounts of liquid water to lubricate plate boundaries. It may also require a large moon to stabilize its rotation and generate strong tidal forces. Earth happens to meet all of these requirements, but how many other worlds do? Stern and Geria estimate that the fraction of habitable planets with long-lasting plate tectonics, significant continents, and large oceans could be somewhere between 0.00003 and 0.002. That is an incredibly small number. Even at the optimistic end, it means only about 2 out of every 1,000 habitable planets would have the right geological conditions. When this factor is included in the Drake equation, the expected number of technological civilizations in our galaxy shrinks dramatically. Instead of thousands or millions of advanced species, the result could be close to 0, perhaps 1, perhaps less than 1, meaning we might truly be alone. And there is yet another problem that makes the situation even more challenging. Even if life does exist elsewhere, even if it is relatively common finding, it may be extraordinarily difficult. So far, astronomers have discovered more than 5,000 exoplanets. For many of them, we can determine basic properties like mass, size, and orbital period. In some cases, we can even analyze their atmospheres using a method called transit spectroscopy. When a planet passes in front of its star, a tiny portion of the starlight filters through the planet's atmosphere. By studying the resulting absorption lines, we can identify certain gases. This technique has already allowed us to detect water vapor, carbon dioxide, methane, and even elements like sodium in the atmospheres of distant worlds. In theory, we should be able to identify signs of life on distant planets by looking for what scientists call biosignatures, gases in an atmosphere that strongly suggest biological activity. One of the clearest possible indicators would be the simultaneous presence of oxygen and methane. On Earth, these two gases exist together in a state of chemical imbalance. Oxygen and methane naturally react with each other. So if both are found in significant amounts, it means something must constantly be replenishing them. On our planet, that something is life. Plants and photosynthetic organisms continuously release oxygen, while various microbes produce methane as a byproduct of their metabolism. Without living organisms actively maintaining this balance, both gases would disappear in less than 10 million years, a very short time on geological scales. So, if astronomers were to discover oxygen and methane coexisting in the atmosphere of an exoplanet, it would be a powerful clue that life is present there. It wouldn't be absolute proof, since certain non-biological processes can sometimes mimic these signatures, but it would be extremely compelling evidence. The problem is that, so far, we haven't found anything like that. And the main reason is technological. Most of the exoplanets we've detected up to now are either massive gas giants similar to Jupiter, or they orbit very close to small, dim stars. Both of these situations make it extremely difficult to analyze their atmospheres in detail. The launch of the James Webb Space Telescope in 2021 marked a major step forward. For the first time, we have an instrument powerful enough to potentially detect biosignatures on small, rocky planets around nearby stars. We are finally entering an era where finding signs of life is within reach. But up to this point, we still haven't detected any. And the longer we continue searching without success, the more meaningful that cosmic silence begins to feel. Even if we eventually do find biosignatures, suppose we discover oxygen and methane on several nearby planets, that would only tell us that simple life exists elsewhere. It would not tell us that intelligent life exists. To detect intelligence, we need something different: technosignatures, evidence of advanced technology. And this is where the challenge becomes even greater. On Earth, human civilization has been producing detectable radio signals for less than a century. Our first large-scale radio broadcasts began in the 1920s. That means the sphere of space where our signals could be picked up, the so-called radio bubble, has a radius of only about 100 light-years. The Milky Way galaxy, by comparison, is roughly 100,000 light-years across. Our radio bubble, therefore, occupies only about 1/1,000,000th of the galaxy's total volume. If another technological civilization exists somewhere in the Milky Way, and if they reached a similar level of development around the same time we did, the odds that their signals would overlap with ours are incredibly small. And that assumes civilizations continue broadcasting powerful radio waves for long periods of time. In reality, we are already moving away from that phase. Modern communication increasingly relies on fiber optic cables, tightly focused satellite transmissions, and directed digital signals. As a result, Earth is gradually becoming quieter in radio terms. 100 years from now, our planet might be almost invisible to traditional SETI searches. If most civilizations follow a similar path, if they only have a brief window of strong radio emissions lasting a century or two, then even a galaxy filled with thousands of intelligent species might appear completely silent, simply because their active periods never overlap. There is also the enormous challenge of knowing where and how to listen. The electromagnetic spectrum is vast, and we have only explored a tiny portion of it. We have scanned a small fraction of the sky at limited frequencies for a relatively short time. It's a bit like dipping a cup into the ocean, finding no fish inside it, and concluding that fish don't exist. Despite all these limitations, I still believe the lack of any clear detection matters. We have been actively searching for extraterrestrial signals for more than 60 years. We have surveyed millions of stars. If intelligent civilizations were truly common, we would expect to have stumbled upon something by now, a stray transmission, an unusual pattern, some unmistakable anomaly. Yet we have found nothing. That silence suggests several possibilities. Perhaps civilizations are extremely rare. Perhaps they tend to remain quiet. Perhaps they don't survive very long. Or perhaps they communicate in ways we cannot yet imagine. At this point, you might reasonably object. You might say, "Lenny, you're thinking too narrowly. You're assuming life elsewhere must resemble life on Earth. Maybe intelligence doesn't require plate tectonics. Maybe it doesn't require oceans and continents. Maybe silicon-based organisms living in ammonia seas on a tidally locked planet could evolve intelligence in completely different ways." And that would be a fair criticism. We only have one confirmed example of life. To study Earth and drawing universal conclusions from a single data point is always risky. But here is the reality. We can only base our reasoning on what we actually know. And what we know is that on our planet, the emergence of intelligence required billions of years of evolution, very specific geological and environmental conditions, a series of mass extinctions that reshaped ecosystems, and an enormous amount of luck. Perhaps there are alternative routes to intelligence. Perhaps some worlds can produce advanced civilizations under entirely different circumstances. But at the moment, we have no evidence for that. And without evidence, the most rational assumption is that the path that led to us is either necessary or at least extremely difficult to replicate. Let me bring up the idea of the Great Filter, because it plays an important role in this discussion. The concept was introduced by economist Robin Hanson. The basic notion is that somewhere along the long chain of events, from the formation of a planet to the rise of a galaxy-wide technological civilization, there must be a major obstacle, a bottleneck that prevents most life from ever reaching advanced stages. The crucial question is this: where exactly is that filter located? Is it something we have already passed, or is it something still waiting for us in the future? If the filter lies behind us, if the truly difficult step was going from chemistry to simple life, or from simple life to complex life, then we may have already overcome the hardest barrier. In that case, the path ahead might be relatively open. But if the filter lies ahead of us, then the situation is far more troubling. It would mean that most intelligent civilizations manage to arise, but then fail to survive long enough to expand beyond their home world. There are many possible ways a civilization could collapse before reaching the stars: nuclear conflict, runaway climate change, uncontrollable artificial intelligence, global pandemics, asteroid impacts, or technological disasters we haven't even imagined yet. What makes this idea especially unsettling is that we see no clear evidence of any civilization that has successfully made it through that filter. The galaxy appears empty. No one has spread across the stars. No one has left behind traces that we can detect. That leaves us with two main possibilities. Either the Great Filter is behind us, which would imply that intelligent life is extraordinarily rare, or the filter is ahead of us, which would suggest that most civilizations, including ours, are unlikely to survive long enough to become truly interstellar. Personally, I hope the first option is correct. I would rather believe that we are rare than believe that we are doomed. But at the moment, the available evidence doesn't allow us to choose confidently between these two interpretations. Now, let me respond to an argument I hear very often, the argument based on large numbers. People frequently say to me, "Lenny, the universe is unimaginably huge. There are countless stars and planets. Even if the chance of intelligent life on any given planet is extremely small, there should still be many civilizations out there simply because the numbers are so enormous." For a long time, I found that reasoning convincing, but I don't anymore. Here's the problem. The size of the universe doesn't help if the probabilities are small enough. Suppose, for example, that the chance of intelligent life emerging on a habitable planet is 1 in 10 to the 21. Even if there are billions upon billions of potentially habitable worlds, that probability would still imply fewer than one technological civilization in the entire galaxy. And we have no real way of knowing whether such a number is too pessimistic or too optimistic. The true probability could be 1 in 10 to the 50, or 1 in 10 to the 100. We simply don't know. The key point is this: large quantities do not compensate for extremely tiny odds. Think of it like a lottery. Imagine the chance of winning is 1 in 300 million. If you buy 1 billion tickets, your odds certainly improve, but you are still very unlikely to win. That is essentially the situation we face with intelligent life. Yes, there may be billions of planets, but if the odds of any single planet producing a technological species are low enough, those billions don't change the conclusion. This perspective also connects to my own research on the string landscape and the anthropic principle, which I believe offer a useful way of thinking about our place in the cosmos. In the multiverse framework that I have worked on, particularly the idea of eternal inflation, populating a vast landscape of possible universes, there may exist an almost unimaginable number of different cosmic regions. Theoretical physics suggests there could be something like 10 to the 500 distinct possible vacuum states, each corresponding to a universe with slightly different physical constants. Most of those possible universes would be completely lifeless. The values of their physical parameters would not allow for stable atoms, long-lived stars, or complex chemistry. They would be sterile, empty, and incapable of producing anything like biology. In many possible universes, the basic physical conditions would simply be wrong. The cosmological constant might be too large, electrons might be too massive, carbon might never form, or chemistry itself might be impossible. We happen to exist in one of the very rare universes where the laws of nature happen to allow life to exist at all. That is an example of observer selection. We could not find ourselves in a universe that doesn't permit life, so naturally we observe one that does. But that raises a deeper and more important question. Even within a universe like ours, one with the right physical laws and constants, how frequent is life? And beyond that, how frequent is intelligence? The multiverse idea may help explain why our universe has the right fundamental properties, but it says nothing about how likely intelligent life is within this particular universe. It is entirely possible, and perhaps even probable, that even in a life-friendly universe like ours, the actual emergence of intelligent beings is so improbable, so dependent on very specific conditions and random events, that it might occur only once per galaxy, or even only once in the entire observable universe. The anthropic principle explains why we are here at all, but it does not guarantee that there should be many others like us. This distinction is sometimes described in terms of the weak and strong anthropic principles. The weak version simply states that we observe a universe compatible with our existence, because otherwise we wouldn't be here to observe it. The strong version, on the other hand, suggests that the universe must somehow be structured to produce observers like us. I accept the weak version, but I remain skeptical of the strong one. If that skepticism is justified, then the fact that intelligent life exists on Earth does not imply that intelligent life is widespread. It only implies that it has happened at least once. Think again about the lottery analogy. If you win the lottery, that doesn't prove that many other people also won. It only proves that someone won, and in this case, that someone happens to be you. We may simply be the winners of a vast cosmic lottery. We live in a universe where life is possible, on a planet with just the right geological activity, just the right history of oxygen buildup, just the right sequence of evolutionary accidents and extinctions, in the right type of galaxy, at the right moment in cosmic history. None of that necessarily means there are countless other winners. It might only mean that we were extraordinarily fortunate. And this leads to an idea that I find both awe-inspiring and deeply unsettling. Observer selection might actually be hiding our true uniqueness. If intelligent life is incredibly rare, perhaps even unique in the observable universe, we would still expect to find ourselves in exactly the situation we see today. We would naturally appear on a habitable planet, in a life-permitting universe, surrounded by an enormous and apparently empty cosmos. That is the only kind of environment where observers could exist in the first place. Whether the universe contains a million advanced civilizations or just one, our personal experience would look almost identical. From our perspective, we would still be here, wondering if anyone else is out there. This is profoundly disturbing to me. It means that the evidence we currently have our own existence, combined with the silence of the cosmos, can be interpreted in two completely opposite ways. It is consistent both with the idea that intelligent life is common and with the idea that we are entirely alone. At least for now, we have no direct observational way to decide between those possibilities. All we can do is reason from what we understand about biology, geology, and the history of life on Earth. And when I look carefully at that evidence, it leads me to conclude that intelligent life is probably extremely rare. There is one final point I want to address, and that is the question of timing. The universe is roughly 13.8 billion years old. Our sun and solar system formed about 4.6 billion years ago, and Earth itself is about 4.5 billion years old. In cosmic terms, that makes us relatively young. Many stars formed billions of years before our own. In principle, civilizations could have arisen elsewhere long before humanity ever appeared. If civilizations had emerged billions of years ago, and if they had developed interstellar travel, they would have had more than enough time to spread across the entire galaxy. By now, the Milky Way should be overflowing with their colonies and descendants, yet we see no trace of anything like that. This line of reasoning is often referred to as the Hart-Tipler argument. Physicists Michael Hart and Frank Tipler independently suggested that the very absence of extraterrestrial visitors on Earth is strong evidence that advanced alien civilizations do not exist. Their logic was simple. If such civilizations were out there, they would have expanded through the galaxy long ago, and we would already see clear signs of them. Of course, there are possible counter-arguments. Maybe advanced species choose not to colonize other worlds. Maybe they prefer to remain on their home planets. Maybe they are present but intentionally hiding. Maybe they visited Earth in the distant past and we simply missed it. But all of these explanations require special assumptions. They depend on the idea that every alien civilization, without exception, behaves in a very specific and somewhat unlikely way. The simpler explanation following Occam's razor is that there are no civilizations spreading through the galaxy because there are no civilizations at all. Intelligent life may simply be too rare, perhaps even unique to Earth. However, the timing issue deserves a bit more careful thought because the situation may be more complicated than it first appears. The very first stars in the universe, known as population 3 stars, formed only a few 100 million years after the Big Bang, but those stars were composed almost entirely of hydrogen and helium. They contained no heavy elements, no carbon, no oxygen, no silicon, no iron, nothing beyond the simplest atomic building blocks. Without heavy elements, you cannot form rocky planets. Without rocky planets, you cannot have complex chemistry. And without complex chemistry, you cannot have life as we understand it. All of the heavier elements that make planets and biology possible were created inside stars through nuclear fusion and then scattered into space when those stars exploded as supernovae. This process, called stellar nucleosynthesis, takes an enormous amount of time. Multiple generations of stars had to be born, live out their lives, and die before the universe contained enough heavy material to build Earth-like worlds. As a result, the first truly rocky planets probably could not have formed until the universe was already several billion years old, perhaps not until 6 or 7 billion years after the Big Bang. And even once rocky planets began to appear, the early universe may still have been a difficult place for life to survive. Supernova explosions were more frequent. Gamma-ray bursts were more common. Radiation levels were likely higher. The overall environment may have been far more hostile than it is today. It's possible that the so-called galactic habitable zone, the region of the galaxy where conditions are suitable for complex life, was much smaller in the distant past, or may not have really existed at all. So even though the universe is 13.8 billion years old, the actual window of opportunity for intelligent life may have opened only in the last few billion years. If that is true, then we are not strangely late to the cosmic scene. We may actually be relatively early. It could be that we are among the very first technological civilizations to arise in our galaxy, perhaps even the first of all. And if that is the case, then the silence of the universe becomes much easier to understand. There are no ancient galaxy-spanning civilizations because there simply hasn't been enough time for them to develop. In that sense, we might be pioneers, the first explorers, the first minds capable of wondering about the cosmos. Perhaps we are the first eyes through which the universe has begun to look at itself. That idea is certainly inspiring, but it doesn't completely resolve the Fermi Paradox. Even if we are among the earliest civilizations to appear, we would still expect at least a few others to be emerging around the same time. Stars like our Sun formed in large numbers. Planets similar to Earth must have formed under similar conditions. So, where are they? Unless the explanation I keep returning to is correct, that the obstacles are simply enormous, that the filters are so severe that intelligent life is extraordinarily rare. Perhaps there is only one technological civilization per galaxy, perhaps only one in 100 galaxies, perhaps even fewer. If that is the case, we could be alone for an unimaginably long time, maybe forever. When I was younger, I was much more optimistic about SETI, the search for extraterrestrial intelligence. I believed we would eventually pick up signals from other civilizations. I assumed that the universe must be full of intelligent beings, all communicating and exploring just as we hope to do. But we have now been searching for more than 6 decades. We have examined millions of stars. We have studied thousands of exoplanets. We have scanned the sky for radio transmissions, optical pulses, infrared anomalies, every kind of technosignature we can think of. And we have found nothing, not a single confirmed signal, no unmistakable sign of advanced technology, no alien megastructures, no directed messages, no accidental leakage, just silence. At some point, that silence has to be taken seriously. There comes a moment when the absence of evidence begins to look very much like evidence of absence. I'm not suggesting that we should give up the search. Far from it. We should absolutely continue listening, observing, and exploring. SETI remains a worthwhile and important scientific endeavor. But I do think we need to prepare ourselves emotionally and intellectually for a difficult possibility that we may truly be alone. That intelligent life is so rare, so dependent on fragile chains of events, that it might have appeared only once in the entire observable universe here on Earth. If that turns out to be true, then the implications are profound. It would mean that we carry an enormous responsibility. We would be the only beings capable of asking questions about existence, the only minds able to study the universe, to create art, music, literature, and science. We would be, quite literally, the universe's only known way of becoming aware of itself. And if we were to destroy ourselves through war, environmental collapse, or reckless misuse of technology, then that spark of awareness could vanish completely, perhaps for billions of years. That is a heavy burden to bear. But it is also, in a strange way, deeply motivating. It means that what we do truly matters. The decisions we make as a species matter on a cosmic scale. If we are the only intelligent life in the galaxy, or even in the universe, then protecting our civilization, preserving our planet, and eventually expanding beyond it becomes more than just a human goal. It becomes a responsibility to the universe itself. Let me finish with this. I could be wrong about all of this. In fact, I sincerely hope I am. Nothing would make me happier than to wake up tomorrow to the announcement that an unmistakable alien signal has been detected. But based on everything we currently understand, based on the Drake equation, on the geological history required for complex life, on the rarity of intelligence, and on the overwhelming silence of the cosmos, I have to conclude that intelligent life is probably extremely uncommon. We might truly be the only ones. And if that is the case, then we must take care of ourselves, take care of our world, and take care of our future. Because if we are the universe's only chance at intelligence, we simply cannot afford to fail. Thank you for listening. Tonight, when you look up at the stars, remember this. We might be the only ones out there who are looking back.